Good evening and welcome everybody. My name is Obi-Wan Pez and this is N-Simplex Pachinko, and tonight we're going to do our differential equations class, night 18 if you can believe it, on specifically LaPlace Transforms, where we're going to look into a few reasons as to why these things exist and some of the implications that go a little bit beyond just strictly differential equations. We do want to just have a little introduction primer in terms of like what the motivation behind it is, and then eventually we'll get to apply them to differential equations. Most likely that will be the latter half of the evening, and we'll see how it goes. And joining us tonight we have Zach at e to the 2i pi. If you'd like to introduce yourself.
Yeah, I'm Zach. I'm e to the 2i pi, and I stream math, and we're here to do some differential equations. I'm here to help out.
And
Also, what's up, Omnifitus? About one-sided Fourier analysis. In some ways, yes.
And if there's anything you'd like to celebrate, let us know.
I mean, there's lots to celebrate, but I finished a PhD dissertation defense, or the proposal defense. So we're in the final stages of that. We just started Infinite Series, the first night of a 11-week course, twice a week, sort of in the spirit of this one that Obi-Wan Pez is doing. Running that over on e to the 2i pi. So if you want to join us, we had a good discussion last time. Go check out that if you're interested.
Yep, and let's see if it's actually working tonight. Are you doing that on your Discord?
Yes, I am.
Okay. Hey, EnigmaBot's working tonight, so...
Let's go. Let's go.
So if you'd like to join Zach's Discord in order to join in the class, or just watch on Twitch, hang out with a nice community, we got a bunch of us over there, and we are currently using Penn Center's Discord server as a repository for this class. So if you have any questions, if you want to look at some of the items that we're doing here on stream, if you want to go over stuff on the VOD, what have you, then you can go to Penn Center's. All right. So I think first thing tonight is we're talking about integral transforms. So first off, I guess, what is an integral transform? And why is it useful? Zach, do you want to speak to any of that?
Oh,
or...
okay.
No, that's sorry.
Yeah, I don't know. I didn't know if that was a cue to talk or if that was what that was.
Go for it.
So typically, an integral transform, I mean, it has an integral in it, so we're transforming from one space to another in a very simple way. And the transform typically has what's called a kernel, which is sort of this null space, or this kernel thing that we traditionally say a function. It's the function that maps to the zero, or the identity, the zero identity. But in our case, when we talk about integral transforms in differential equations, the most common integral transform is to use some exponential function, though there are others you could use. But you're multiplying the function f of x with this other kernel function.
Is fx dx, yeah, okay. Oh, right, I need to change it for this one because I don't want to mix variables. Alright, so for our LaPlace transforms specifically, we're going to take our original function f of t dt, and normally we're trying to do some sort of integral between a and b on f of t dt, but turns out it's not going to work for us for one reason or another. Maybe it's the wrong kind of function, maybe it's just got, too much stuff that's in it. Anyway, it's not working for us, so we decide, okay, well, if we multiply this by some other function, again, as Zach said, it's going to trade spaces and put us into a different space, and in doing so allows us to potentially change the nature of the function that we have, which then hopefully will end up allowing it to be solvable. So yeah, the kernel that we're multiplying in is usually going to be on some other variable, usually s, and then whatever variable we're starting with, x or t or what have you. And most of the time we're going to denote this as taking the Laplace transform of f of t. Yep. Alright, so k is a kernel function. And I've also heard it called a nucleus.
That's fine. I've called it a kernel, but I suppose nucleus works.
I'm gonna call it a kernel because that's the only one I've actually heard used, but I found out that nucleus was a thing in doing a little bit of research for it.
Yeah, I was gonna say I've not heard of it. I've not heard of nucleus, but that I guess that works.
Yeah, I just wanted to make sure my terminology was up to date, I guess. Alright, so then there are going to be a whole bunch of other potential integral transforms, and here we see, I just put a link in the chat for the wiki page that has, I want to say it's on the order of 30. Oops, wrong one. Yeah, 20. I've only seen probably one or two of these actually used, like, in my experience, but it all depends on what precise use case you have for whatever integral you're trying to take.
Pretty much. A lot of what I've used also have been the Fourier transforms. Those are more useful for partial differential equations.
Mm-hmm.
But other than that, most of these other ones that I'm looking at that page, not very often I see those. I've used the Poisson kernel before, but again, the Mellin transform can be useful. I've seen it written in theory, but all these other ones, like the Mellin transform, I've seen in or Mellin. I don't know how they say that. I've only seen it written, so I've never seen it said out loud. But that one is related to the gamma function and a few other things. So, but it's related to the Z transform in I believe, if I remember correctly, in electrical engineering. But that's not what we're talking about tonight.
Hey, Alec. Good evening. Yep. So, whereas there are many, right, we're going to focus on the one specific one that is the most used in at least ordinary differential equations. So, and under what cases do we typically see Laplace transforms being used?
Well, so it's interesting because I want to talk a little bit about like what this means. This was actually mind blowing when someone pointed this out to me.
Absolutely.
But when I saw the integral sign and like this e to the minus st, I was like, what the heck makes you think of that function? Why on earth would I use an integral here? And why on earth would I do that integral from 0 to infinity, right? Like what am I trying to accomplish?
Mm-hmm.
And this is what when I ran differential equations classes on my campus, or at least I only ran one, so I shouldn't say I ran multiple, I ran one. What we talked about was how there's a sense of resonance that's important, and that this thing is actually a measure of resonance with e minus st as the kernel. So if you think about the function, say e to the minus 2t, say I were to do that integral and calculate this thing, I'm going to get something that is 1 over s plus 2, if I did that correctly in my head. And the reason you're going to get that is because that is the s value with which e to the minus 2t resonates, right?
Yep, that makes sense.
Okay, and so that's the value of s that will, like, that's going to be the 0. So we're basically taking this and making an algebra problem out of it in the complex plane. And the zeros and the poles of the function we get out are going to represent the places of resonance. So what's cool is that when you think about this integral, you're actually summing all possible values of s against your function and figuring out which of those resonate in essence, right? I like to think about this in terms of inner products, and we may get to talk about a little bit of this in infinite series. Like there's some relevance here with what's called the Fourier series, and there's some fun things we get to talk about there if we can get to it. But it sort of depends on the needs and desires of our class. But that's the idea.
That makes f of t resonate, you think, or?
Well, no, it is, and so
finds the s value.
Sure.
At which?
That's right. Yes.
Not which makes, really.
Right. Which causes resonance. Another example, say you have like a cosine function in there as f of t. Well, what it's going to do is give you that requires that the s value had to be complex. Right?
Mm-hmm.
And so you're going to get a complex denominator. You're going to have some s squared plus something, which is not you can't decompose that.
Right. That's going to be complex,
makes perfect
strictly
sense.
Complex, yeah.
You'll have poles in the imaginary plane, or in the imaginary axis in some way. And if you have some combination, some product of exponential and sinusoid function as f of t, you're going to get some s squared plus something, but then you're going to have a translation in the real axis, depending on what the real part of the exponential part does. That's sort of conceptually what this is trying to encode. Which is why do we choose this kernel? This kernel resonates nicely with all damped sinusoids, right?
Very nice.
And so if I'm looking for a damped sinusoid, this makes a logical choice. I've always wondered that. It took me forever to be like, what? I had to think about this hard and I did some I think it's illustrated if you do like some simple like exponential and sinusoid integrals just to illustrate the point.
Definitely.
And that's what we did in the class. Is like in the class I taught, we started just building the Fourier or the Laplace transform table from scratch, and said let's build some of the properties that this has. Oh look. It has this nice thing that if I throw in an exponential function for f of t, I'm going to get, as you'd expect, a pole on the real axis.
Mm-hmm.
And so this real axis encodes something about the exponential damping of our function, or growth, as the case may be.
Right. That's pretty cool. Dr. Cook, good evening. You can think of these integral transforms as a change of basis on infinite dimensional function space. Fourier transform, for example, is a change of basis that diagonalizes the derivative operator. Oof.
There's some crazy stuff like that. I mean, there's some deep theory here that Dr. Cook, I believe, is correct here. I know, like, that sounds like a fact I learned in one of my differential equations classes somewhere. It's not something I use very often, but it is that's a really neat fact. And this is why I think that the Laplace transform is a very powerful tool, because it tells us something about the nature of our solutions. Like we can it's almost like a sledgehammer that solves second order ODEs and nth order ODEs that are reasonably nice very well.
Yeah.
And it ties all the ideas of the course together, saying that basically whenever you solve a differential equation, E is always the answer. That was the first thing we talked about. Like, the answer was always E, and E is always the answer. And when you don't think it is, think about Euler's formula, and then you realize, actually, E is always the answer. And what's fun is when you do dynamical...
It's just how, complexly it is encoded into the function that you have.
And when you have a system of differential equations, E is still always the answer, because you take E to the diagonal matrix, right? And multiply things as appropriate. So I stand by what I said, and people can fight me in chat if you like. I mean, I'll put a little asterisk there for a few special cases, but I think it fits the majority of what students encounter.
Omnifidus also says the Z transform was not mentioned on the integral transform page, and that may also be useful. Awesome. Alrighty. Okay, so one simple answer to the question, when might we use Laplace transforms, is going to be always. But as you said, Zach, it's a bit like using a sledgehammer. Do we necessarily need to use a sledgehammer all the time? Not necessarily, but probably gets the job done no matter what.
There are cases it won't get the job done. I can say that, like.
Oh, okay. Yep.
Like there are times, like, I know you talked about series solutions, for instance, and those are cases where you might have to not use a Laplace transform. It's not as convenient, at least.
Yeah.
I'm sure you probably could do it if you tried hard, but it's not worth the effort, in my mind.
All right, so I would say most likely use cases when the other stuff that we've tried so far has either failed or become unwieldy. When would we want to use the Laplace transform above the other stuff?
Well, I know this is jumping the gun a bit, but I'd say the word convolution, but I'm not sure we're ready for that yet.
Well, let's go for it. So what's convolution?
So, do you want to go there right now? Because I wasn't expecting to go there that quickly, but okay.
Well, I mean, we can throw it out there. Just what's the simple definition first, and then we'll worry about more complex stuff later.
That's good. Well, yeah, I was going to say this can get complicated fast. And there's some neat blog posts that explain this really well, and I know Grant Sanderson has made a video a little bit about it.
Mm-hmm.
But in principle, like, the formal definition is that when you take two functions and convolve them, you're doing an integral. And I guess we could do this over the real numbers, or from 0 to t. I guess we do it from 0 to t because we're doing this on a one-sided Laplace transform, which is the default. So of f of tau times g of t minus tau, d tau.
Sorry, integral of g of tau.
Sorry, let's do f of tau. I suppose it doesn't matter too much.
Yeah.
but f of tau times g of t minus tau, d tau. That's the t minus tau. T minus tau, because you're doing a shift.
Right. Yeah, and this is in the table, certainly, that we look at when we're trying to figure out LaPlace transforms by itself. So here again, this is shifting g by tau, which is going to be just going to be the new argument of f when we get into it. But yeah, we're not going to really touch convolution in this particular treatment, just because it is typically a little bit beyond where my undergrad course goes. But we can also touch a little bit on it.
So
probably.
I mean, I have a excuse me.
No, that's right.
I have a blog post that I can show you on
Absolutely.
something that will it's on a website called Better Explained, and it does a really good job. Here's the basic principle, and Syntax is asking in the chat, so I think this is sort of useful to talk about. It's a useful property, but imagine the analogy in this thing says, imagine you're at you go to the hospital and you have you're administering a medicine that takes multiple days to take effect, and you have multiple doses that you have to take per day. So like say if you go to the hospital for a certain illness, it takes like 3 doses the first day, 2 the second day, and 1 the third day, right? Mm-hmm. So if I go in to the hospital and I'm tracking how many people need to have, like let's say I have a certain number of people come in on a Monday, and there's like 10 that come in for stuff, and then 12 come in the second day, and 4 come in the third day, and I have this list of people. Well, I need to create a dosage schedule, right? Because on any given day, like I need to be able to make a total number of doses needed. And so what this convolution does is it says, how can I take the sum of all of the different dosage requirements for everybody over the course of the 5-7 day whatever period? And the way we do that is we basically reverse index everything. We basically like take the 3, 2, and 1 doses, start at either the front or the back, and move one of the lines, sort of cascade adding. This is hard to show without a picture. I'm trying to get the actual the thing for you, and it turns out this website is unfortunately down. But the idea that's the discrete version. You just generalize that to a continuous thing. So you're finding. So basically, we're doing an index shift with the purpose of summing, and then if I take the continuous analog, that's the integral version. What I described as discrete, so you just be doing a sum.
Right. You can only take certain amounts of medicine at certain moments in time. Right. It's not.
There's that one, and then there's another one by Grant Sanders that talks about convolution in the context of what's called a Borwein integral. And it's a sort of interesting application as well. So I'll let you, I'll try and find these. Here it is. Grant has a 23-minute video if you want to take a look at this as well. I like Grant's explanation with filters, and this is like a practical application where you use filters for image processing. And there's something called the Gaussian filter, which you're basically doing a convolution on every pixel in an image to try and blur the image. And it's a really cool idea and a cool application of the idea.
Nice.
So it's where the phrase Gaussian blur I think comes from. So I'll put that in Discord.
So many of us have done stuff like that on Photoshop and probably never realized what was going on behind the scenes, actually.
That's right. So
All right. Well, thank you.
And I'm gonna put this on. This is like, if we only got, when I taught the class, we got like half a class period to be able to discuss this. So there was no way I was gonna be able to do anything but the basics. We couldn't even talk about some of the stuff I'm talking about here. I like told the hospital example as a story and was like, here's what it does. I'm gonna put a question on your final, just a basic computational question, and that's it. We just didn't have time to go into it deep.
Yep.
So.
Is there any
There you have
consistency
it.
on transform notation? Mellon transforms usually marked as M block F of T of S. Oh, right, M. Your curly brackets are not function notation. Right. It's probably a lower
I found it. Okay.
subscript.
Found the thing. I found the thing. So it's on Discord.
Yeah,
These
so
two
syntax,
resources.
the like LaPlace transforms, they don't put S in the statement of it just because it's always e to the negative st as the kernel function. So I'm sure that there's we talked just a little bit ago about typically you're going to see the kernel k of s comma x times f of x dx inside the integral, but you know there's the possibility that there's a different way for every single one. And especially in terms of notation, like this is the one that I mostly have experience with, not being a research mathematician.
So here's one other fun fact. If you want to conceptualize this, the multiplication algorithm itself, when you do the traditional multiplication algorithm, that is a convolution. Which is another fun example that you can illustrate, because you're shifting digits, right? You're multiplying with different place value, and in and of itself, that is a convolution. This article goes into some detail, talks about it, but that's an example. You have to take every place value in the first number and multiply it by every place value in the second number, which is essentially, you know, a form of this. What am I trying to say? This shifting of one array over another.
Syntax wants to know, are there any integral transforms that don't have bounds?
So, not that I've encountered. That's a really good question.
Yeah, me neither. I've also seen some that go from positive to negative infinity, or negative to positive, or 0 to infinity like Laplace, or A to B, I guess. But Zach, go ahead.
No, it's fine. I can't think of an. I really can't think of one. Yeah, I'm trying to see if there's any. Yeah, I don't see anything.
Yeah, so in my notes I have that k of st is going to be the kernel of the transform, and alpha and beta, which are the limits on the integration, are going to be given constants. So,
and omnifidus is correct, like negative infinity to infinity. I thought the spirit of syntax's error is more in syntax errors comment is more about not having bounds at all, like an indefinite transform, if that makes sense.
Yeah.
I think that's how I was interpreting it. Like, sure, the negative infinity to infinity is unbounded for sure. But yeah, I don't know of any that don't have bounds at all.
Yeah. So like something like e to the negative x squared dx, right? That'll allow us to have an infinite, like any finite block, or we can continue to either infinity. But yeah, syntax is definitely, as far as I interpreted, was going for the indefinite integral. Alrighty. Lively discussion. Alright, good stuff. So when we're typically talking about using Laplace transforms in differential equations. So the usual one that I'm looking at is the system is either discontinuous or impulsive. So for instance, we were talking earlier about a spring mass system, which might have something like y double prime plus, what was it, or gamma y prime plus, kx, or ky, I guess in this case, is equal to f of t. And our f of t was going to be the forcing function. So when we say like an impulsive system, usually that forcing function is going to be working on the function only like over a specific time period, and then it's just going to stop. So we're going to allow our function to have 0 value, suddenly have whatever value it's going to have, and then again suddenly have 0 value again. So this is going to be our t and f of t. Okay. Anybody want to speak to that? Alrighty. Some other helpful stuff comes up. And first of which is the integral transforms, specifically, again, Laplace, but this should work in this should still work in many other respects. Are going to be linear operators. Such that if we're taking the Laplace transform of f plus g, we're going to get their individual Laplace transforms. Laplace of f plus Laplace of g. And also if we take the Laplace of some constant times f, we end up with the same thing as the constant times the Laplace of f.
And most of these are inherited from our from the properties of integration.
Right. And putting these together, this also means that linear combinations are possible. So here we have the Laplace transform of C1f plus C2g is going to be identical to c times the Laplace of f plus c1, c2 times the Laplace of g. And this kind of goes with the principle of superposition that we were talking about a while back, where like if we have individual solutions to differential equations, we could then say that the linear combination of that thing is also going to be a solution, or of those two things is going to be a solution. Here it's going to be Laplace transforms that we're talking about, and if we're taking Laplace transform of the linear combination, then it's the same as a linear combination of the individual Laplace transforms. Now add all this convolutional stuff. Yeah, cool. I know if I know A, which is a transform of f of t, can I with that result get the transform of B? You know how they behave. I'm not. I don't know if I can touch that one. Zach, you have any insight on that one?
Not off the top of my head. To be honest with you.
All right. If typically we're going to call the Laplace transform of f of t, we're just going to call that capital F of s. Then what we're going to see is when we take the Laplace transform of some other, and in this case we could look at what Zach was saying, some other exponential function times f of t. Actually, that's not what you were saying earlier, sorry. So in theory, we could go through a whole bunch of the properties that we see here. All of the individual function types, we can at least poke around with a couple of these and see how they work. Anything that's exponential, if we're bringing this into the Laplace transform form, then what we're seeing here oops. I think I'd be used to that by now. Is that right, capital F of s is going to be equal to our integral 0 to infinity of e to the negative st times, and here we have e to the at times f of t dt. Right, in this particular case, we look at this and we say, these are exponential functions, so they're going to combine. And this is also why, you know, just looking at the Laplace transforms of exponential functions by themselves is pretty nice, because these will combine. So here we're going to get e to the negative st plus at. Right, this is not the original f of s. So here we see that taking this integral is going to produce e to the negative parentheses s minus a. When you factor out that negative, you factor out the t's from both of those things. We end up with that s minus a, and then f of t dt. And this is then going to be the same as capital F, but here we see that we have a shift in s. So this is going to be f of s minus a as the argument of the kernel. So again, anything that has an exponential function in it is going to play very nicely with our Laplace transforms. Okay, and you know what? Let's change the left-hand side there. That is the Laplace transform of e to the at times f of t. Okay. Why isn't that negative s f of s minus a? So the term itself inside of the integral didn't acquire a negative. We didn't get a negative that was here, for instance, right? That would get you your negative f. Yep. Right, that negative was up top there. Okay. Taking the Laplace transform of an integral, going to from 0 to t of f of x dx. So the S, right? Zach had said that earlier we were talking about S as the, essentially the resonance value of that kernel. So in taking the integral on S, we were trying to sum up all of the possible kernel functions that we can put in there. And then it helps to highlight which S value or values are going to cause resonance inside of f of t. So anything with an exponential function, right, it's going to shift over a certain amount and tell you there's going to be a value here, whatever that is. Is it possible there's a different way to write the definition of f of s so that s appears in the definition? I mean, it does. Sorry, I'm not understanding, I don't think. So, like, we've got our s here inside of this definition, where the Laplace transform specifically has a kernel function of e to the negative st.
What Omnifidus might be asking for is saying on the right-hand side of the scripty L of ft,
Yeah.
that should equal f of s, capital F of s. Maybe that's
Okay.
That's what. Yeah, I think that's what Omnifidus is saying. That is somewhat conventional to say that.
Gotcha.
That's fine. There you go.
Thank you. All right. So with this one, we end up with trying to take an integral from 0 to infinity of e to the negative st times an integral from 0 to t of f of x dx. Yep, right. And then that's dt outside of that. Any idea how to explain this one?
So is this the one you're trying to do, the LaPlace transform integral?
Yeah.
Well, I mean, you've got two integrals here, and because they're independent by Fubini's theorem, we can swap the order of integration with no problem. So we should, well, actually, hold on. Timeout. I don't think I can say that because we do have t
There's
there.
a
Never
t there.
mind.
Yeah.
There's a t there. Yeah, so I think this might just be a fault of which variable we chose. Unless that's intentionally t. I want to make sure you intentionally chose that to be t, or is that supposed to be some kind of dummy variable?
No, the x is the dummy variable.
Right, but I'm saying is t intentionally... I guess because you're doing a function of t. Never mind, I'm with you.
Mm-hmm.
Okay.
Because by
I was trying to make sure... Right.
Yeah, by Oi. There we go. Fundamental theorem of calculus. Right, we're trying to say that this needs to be a function of t when we talk about that whole integral.
Sure.
So we're essentially looking for what's the integral of the forcing function first, and then changing its variable up.
Right. This might be helpful. Because, well, think of it this way. We can say that we know that the integral of our function is going to be some antiderivative. That much we do know. Right?
We'll play this game.
I mean, in a way that's all we can really say, right?
Yep.
You're gonna get some. So the integral is gonna be some g of, or sort of be like capital F of t. Right.
Right, but not the other capital F of t, which is the definition of the Laplace transform.
Right. So then you're taking the Laplace transform of that antiderivative.
Right. And I think syntax is probably right here, where we'd want to take essentially, or that would be an easy way to return that capital script f back into lowercase f. I'm not sure it's necessary, but it is one way to work it out.
Right. You might find this page helpful. I just found something that might be helpful to... It had an explanation. That one didn't have a very good explanation. But you might find this helpful. You sort of have to work backwards, though, from what you know about derivatives.
Mm-hmm.
I'm going to take a look at this page. The idea is if you take the Laplace transform of the derivative, or so if you take the derivative of both sides of your integral, you end up with the function f is equal to g prime. And you know an initial condition, right? You know that g of 0 is 0, or f of 0. They define this as, I guess, if we define this as some g of t, that integral, then I can say that g of 0 is 0. And then if you take the Laplace transform of both sides, that's no problem. You know how to take the Laplace transform of a derivative. And then you can take you can define the Laplace transform of our function f as f of s, and then solve, basically. So this page works through the details.
Okay, so that one's really looking
It's hard for me to...
Let's make sure that we do the Laplace transform of a derivative first, and then work back.
Right. That's one way to go about it. One I don't remember, honestly. I hadn't remembered that. So like, these aren't properties I work with very often. Like that one I don't use much at all. When I did solve problems, I usually use the derivative fact more than I use the integral fact, to be honest. And as Syntax was pointing out, when you take the Laplace transform of a derivative, that does use integration by parts, if I remember correctly.
Right, because then you can take the actual integral of what you have there.
That's right.
Antiderivative.
And just so you know, in the next 7 minutes, I'm going to have to get going. Just letting you know.
Okay.
I don't know how much I'll be able to stay until then, but I'm gonna be going sometime in the next little bit.
Yep. Yeah. So when we're working this out, right, taking the integration by parts is going to help to separate these out. Again, we already have a derivative, so let's back that up and use that as our antiderivative. So that's going to be our right, dv that we usually state, whereas this one we're going to let that be our u. Right, so our u is going to be e to the negative st by v, which is then just going to be f of t. Minus the integral of v du. Still on dt, or yeah, still on t, and s is going to be a constant, so that can just get kicked out, and we end up with that negative, well, in this case, positive f s times that integral e to the negative st times f of t dt, and this thing we already know is capital F of s, the Laplace transform of f. All right, and that other part. Right, so infinity going in for t is going to cause that to become 0. And then plugging in 0, yeah, and then plugging in 0 for both of those is going to cause e to the negative s times 0 to become just 1, and then we've got f of 0 for that other part. So that's going to be a negative f at 0 plus that. All right, it's equal to our Laplace transform of a derivative. Yeah, and similarly, this can be done n times for the nth derivative of this. We're not going to go out and actually do it because that'd take a long time. However, taking the Laplace transform of the nth derivative of f of t is going to be s to the n times capital F. Yep. Capital F at S. Whoop. Minus, and then all of our lower termed S powers, or lower order S's, are going to be multiplied by our F at 0. Then it's going to be followed by S to the n minus 2 times F prime at 0 minus dot 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 out as far as we need to go. So minus F the n minus 1th derivative also at 0. And that one is times s to the 0, obviously, because we're counting down in our s powers and counting up in our f derivatives. The sum of those things is always going to end up being n minus 1 total, right? So here we have n minus 1 as our power for s and a 0th derivative of f. And likewise, when we move up, we've got n minus 2 as our power for s and first derivative, or 1, for f. Right up. Okay, so then for the... Wow. Okay. Right, so this was saying that S times the Laplace transform of f of t just generally, minus...
I'm gonna have to head out,
0?
but
Yep.
it's good to hear from you, and I'll see you next week.
All right, you too, Zach. Thank you.
Yeah, no problem. Thank you.
And this is going to be equal to f at s. Why am I doing that? Now, as Zach was saying, we're going to essentially choose that our integral function is going to be our replacement f of t in this case, and g at 0 is going to be equal to 0. We can arbitrarily decide because it's going to be an integral function, and so if it's an integral function, you're going to have potentially a plus 0 on the end that we can affix, where the function is going to have its y-intercept. Right, so it ends up that yeah, I should probably change the name of that, just because, right? Let g of t be that integral function from 0 to t of f of x dx with g at 0 being 0. So this means that s times the Laplace transform of the integral function is going to end up being f of s, capital F of s, and then the Laplace transform of that integral function, g of t, is going to be 1 over s times big F at s. Alright, so coming back here, this is going to end up becoming 1 over s times the Laplace transform f at s of the original function. Okay. We're gonna hop on this ad break here, and we'll be back in 3 minutes. Apologies for cutting this short, so we're gonna hit that. Cool. Anybody who's sticking around? Hi. Going to just double check here. Okay, this also means hey, Punching! How's it going? Currently on an ad break for about a minute, just in case. Nice. Grahal, how's it going? My name is Obi-Wan Pez, and this is N Simplex Pachinko. We are doing a class on differential equations, and if you're interested in that level of class, that's what we've got going on, at least for the next hour or so. And then after that, we may... I'm probably not going to do it tonight, but... Sometimes we do any user request in terms of other type of math questions they might have. Otherwise, we do have other friends who do math streaming during the week. These are affectionately known as the Math Chads, ordinary differential equations. So, ODEs. If you want, you can state what your particular background is, what level you're taking, if any, and what you might be interested in. We can try and help you out whenever whenever we have some time for it, or... Okay, so for something as simple as LaPlace transform of 1, in this case we want to take, again, just standard LaPlace transform notation. Here our function is just 1. So this is nice and easy. This is just going to end up being negative 1 over s e to the negative st, because e's derivative and integral end up being the same function times whatever derivative times whatever constant is up with our variable of choice, and integrals we're going to have 1 over that constant. So in this case 1 over negative s, or negative 1 over s, and that's going to be our capital F of s here. Oh, right. Evaluated from 0 to infinity. The e, again, does the exact same thing it did in the last one. The infinity is going to make this 0, so it's gone. So this is going to be negative 1 over s times the quantity, 0 minus, and here when we plug a 0 up top, we get e to the 0, which is going to be 1. So here, this ends up being a positive 1 over s is going to be our f of s. Keeping in mind, if we have any other number other than 1, you're just taking that number and multiplying them on the outside because it's a constant. Makes it nice and easy. Alright, our LaPlace transform of t to the n is going to be similarly fraught with, you know, non-disaster, but still. We're going to take the integral from 0 to infinity of e to the negative st times, in this case, t to the nth power dt. And here, we're going to do the same integration by parts that we did last time. Every single time that we do this, we're going to end up with more and more terms that keep dropping out, and we end up with alright, let's just do 1. We could also do this by induction and say, oh, by the way, this is what happens when we get, you know, n equals 1, n equals 2, n equals 3, and then show what happens at our value is n plus 1, assuming that we know a particular outcome for t to the n. Alright, so here we would take the derivative of t to the n, so we make that u, and then e to the st dt is going to be our dv. So this ends up being uv, so that's going to be to the n times e to the negative st multiplied by negative 1 over s. We know that that's the integral because we just did that back over here. Alright, minus integral of v du, so negative 1 over s e to the negative st times du is going to be n times t to the n minus 1. dt. So this is going to be a positive n over s integral e to the negative st times t to the n minus 1 dt. On the outside over here, this is still evaluated. T goes from 0 to infinity. Again, we're having the exact same things going on. As t goes to infinity, we get t to the n times e to the negative st. So we have a, if we look at the hierarchy of functions, right, our t to the n is going to infinity, multiplied by e to the negative st is going as a whole to 0. So we've got infinity times 0, which is an indeterminate form for a limit, as that's what we're technically doing here. And if we attempt to turn this into, for instance, top being t to the n, bottom being e to the st, we could, 1, say that the exponential function is going to go faster than the polynomial function, and therefore this is going to go to 0 faster. We could, 2, take L'Hopital's rule and try to derive each of those parts. Again, t to the n up top, e to the st on the bottom. E to the st doesn't change, except it gets more and more powers of s. Who cares? Doesn't really change anything. Up top, we get something that's going to keep ticking down. So it's going to be nt to the n minus 1, n times n minus 1 times t to the n minus 2, etc. So eventually, we're going to get t to the 0, and then it won't be indeterminate anymore. We're going to have a bunch of constants up top, and a bunch of constants times an exponential down bottom. That goes to 0 as t goes to infinity. So this whole term is going to go to 0 if t is infinity, and it's going to go to 0 if t is 0. So all these terms end up going away. Why didn't I invoke the gamma function? Because I'm not really a gamma function kind of guy. Alright, similarly, this is going to keep ticking down as well. And so we end up with negative 1 to the nth power. Times Lurg. No, that works. Okay, we're good. This is going to end up being the nth derivative of, with respect to s, of the original 1 over s. So this is going to start collecting values of n and s on the outside of that integral, and it's just going to keep rolling all the way through. Eventually, we're going to end up doing the same integral from 0 to infinity. We end up getting the same value 0 minus 1 that we did back here. right? That 0 minus 1 is going to show up at the end, and we're going to have our 1 over s is just going to keep stacking over and over and over again. So we're going to get another 1 over s on the next time we do this, and the next time we do that, and the next time we do that. And then our numerator, right, is going to accumulate. If we think about how this works, we're always going to get a negative 1 over s multiplier. So our signs are going to switch every time we do this. That's why we get the negative 1 to the n. We're always going to get a higher power of s in the denominator. So that's why we get this like derivative of 1 over s. It's just going to keep rolling through and getting s to the n eventually in the denominator. And then, third part, the n here, and n minus 1, and n minus 2, and n minus 3, etc., are going to keep dropping out of the exponent, and so we're going to get an factorial, n factorial, eventually. Now, we can do that by saying it's n factorial over s to the n, or we could just say, well, that's the nth derivative with respect to s of our 1 over s, which, as it turns out, gives us a secondary property. If we take the Laplace transform of t to the n times any function f of t, we're going to end up with the exact same thing. Negative 1 to the n times the nth derivative with respect to s n times of capital F of s, which is going to be the Laplace transform of the original f of t. I know, that's just crazy talk. Gamma function is shorthand for solving the indeterminate form. Okay, that's fair. Hey Laz, how's it going? Yeah, I don't really know it offhand. Like, I can look it up, I can maybe work with it, but I really haven't done a whole lot of work with higher mathematics in general. You know, I got my degree in math education, and then I went on to a master's in applied math. So, right, and I'm not going to necessarily prove that bit by itself, but you get the idea. This is how all that works. Oh right, and nah, we're good. Never mind. Gamma is a special function. Yeah. Alright. There's all sorts of other cool stuff we could do. We could do, again, I won't show the whole thing, but Laplace transform of sine of AT. So any particular frequency A that's going into our function here for sine, we're going to end up with our integral e to the negative st times the sine of at dt. And in this case, we're going to do the same thing. Right, so we're going to let the sine function be u, and let the Again, e to the negative st dt, b dv. In doing this, we're going to get uv, so sine of at, times negative 1 over s e to the negative st, minus, this is integral e to the negative st times the sine of at. Okay, minus the integral of e to the negative st times, this is the negative 1 over s here, integral of v, and then du is going to be a times cosine of at dt. Then we have to do integration by parts again. So all that stuff still is going to be negative 1 over s e to the negative st, evaluated sine of at, evaluated from 0 to infinity. Right, so this is going to be a negative a over s times the quantity, and we're going to do the same thing, so this is u, this is dv. So uv cosine of at times, again, this is going to be negative 1 over s e to the negative st, minus integral from 0 to infinity. This is evaluated from 0 to infinity. It does get a little repetitive, so, you know, sorry. Take the integral of a cosine, you get a negative sign. So negative e to the negative st. We're taking another integral of this, so that's going to be another negative 1 over s. We're taking sorry, derivative of cosine is going to get us a negative sine at times a there dt. Absolutely. You were able to submit half of your PSATs? No, problem sets. I got you. The only remotely related thing is it says it's graded both for completion and accuracy. Yeah. You know. Yeah, the only reason I'm not doing it, syntax, is just that I don't. There's no real reason. It's fine. If we plug in infinity again, our exponential turns to 0, so that's gone. And then our sine, evaluated at 0, is going to be 0, so that's gone. So that's going to be a 0. Minus a over s cosine of a t times negative 1 over s e to the negative st, again evaluated 0 to infinity. At infinity we get an exponential of 0, so again that's gone. And at 0 we get a positive a over s squared. Nope, it's negative, sorry, because both of those are negative, which makes it positive, but then we're going from infinity to 0. So it's the thing at infinity minus the thing at 0. Okay, there we go. That's better. Then we get a minus a over s integral of e to the negative st sine at a t dt. I'm not touching it because we got that thing here. Integral from 0 to infinity of e to the negative st sine at at dt. So since we got those things, bring them together. Over on the left-hand side, this is going to be a 1 plus a over s times that integral is equal to negative a over s squared. That's it. This is going to be s squared. No. Let's just do s. S plus a, all divided by s. Parentheses left-hand side, yes, thank you. Which I still did it on the next line, just without being careful. Is equal to negative a over s squared. Alright, divide by this thing, so we end up with an s on the top. S on the top over s plus a on the bottom. That is one of those and one of those. That is going to end up with a negative a over s times s plus a. Must mess something up. Hang on. That is not the correct answer. Back up a couple of steps. Yep. There we go. That. Forgot to carry that down to the second row. So that's still going to be negative. But this is going to be a squared over s squared. Whoop. That's still a over s squared. This is a squared over s squared. So s squared, a squared, s squared. And then we take that out of the way. Okay, so s squared plus a squared on the bottom and s squared on the top, which does take out the whole term there. Okay, that's better. Negative a over s squared plus a squared. Okay. And that should be a negative inside, which then translates to an overall negative on the outside here. Cool. So last half hour here, we're going to attempt to solve an actual differential equation. Alright, triple derivative of y plus 3 times the second derivative of y minus the 6 times the derivative of y plus y. It's going to be equal to let's just have it be 1. Right, we'll do a simple one now. We'll do a harder one next class. So with this, if we want to take the LaPlace transform of both sides, right, this is going to get us the LaPlace transform of y triple prime plus 3 times the LaPlace transform of y double prime taps? Come on, man, I'm not that bad. So Zach was saying earlier that this will help highlight like where the resonance is for this particular function. So, for instance, if we don't do this, we're going to need to solve a cubic polynomial equation, which, granted, these days, right, it's pretty much trivial, so whatever. But we're going to have to either factor it or solve it anyway, realistically, in order to do the Laplace transform stuff. So the motivation is going to be that this is not always going to be 1. So later, we're going to do f of t is equal to 0 or 1, depending on where you are. So t is going to belong to the sets, for instance, wow. The sets, right, negative infinity to 0 and 0 to infinity. It's going to turn on at 0 and just stay constant for all time after that. Yes. So transform both sides, solve it, detransform in order to get back to our original function. So yeah, the key that we said back here was really we're going to use for differential equations Laplace transforms if our f of t, our forcing function, is either discontinuous or impulsive. Realistically, impulsive means the same as discontinuous in a certain context, so... Okay. Okay, minus 6 times the Laplace transform of y prime plus the Laplace transform of y. equals the Laplace transform of just 1 for now, which we know is 1 over s. We're going to also go with y at 0 is going to be y prime at 0, y double prime at 0, which is going to be 0. Just makes things easier. Otherwise, we can have it, right? We can have those be whatever values we want. So initial position, initial velocity, and initial acceleration are all going to be 0 in this case. Alright, so from our derivative rule earlier, Laplace transform of y triple prime is going to be s to the third times big Y of t Alright, big Y is just going to be, in this case, the Laplace transform of little y. Oh, no, y of s. Jeez. Big Y of s. It's going to be Laplace transform of little y of t. Okay, so that is s here. Alright, so s cubed times big Y of s. And then we do our minus s squared y at 0 minus s times y prime at 0 minus s to the 0 times y double prime at 0. Alright, then we get a plus 3 times the quantity. Second derivative, Laplace transform of the second derivative of y, same deal. We're going to get here s squared times our big Y of s minus little s times y at 0 minus no s's times y prime at 0. Okay, minus 6 s times big Y at s minus just y at 0 plus big Y at s. That sum is going to be equal to 1 over s. So then we go through this and we say, okay, all of the y of zeros are just going to end up being 0, regardless of how many derivatives they have. Okay, then we have, if we were to take out big Y at s, we're left with a cubic polynomial, s cubed plus 3s squared minus 6s plus 1. That should be equal to 1 over s. We're then going to solve for big Y. So y at s is going to be equal to 1 over s times s cubed plus 3s squared minus 6s plus 1. All right, so for that, then we're going to fall back on our really. Okay. All right, then we're going to try to factor all this stuff, so we're going to fall back on our pre-calculus and say, all right, we've got our we've got our rational roots theorem, which is going to say that if we have any rational roots, it's going to be our constant divided by our leading coefficient, and it could be positive or negative. So with 1, 3, negative 6, 1, you know, can we end up with either a plus or minus 1? That's all we've got for rational numbers. So if it's plus 1, it's going to be 1, 1, 4, 4, negative 2, negative 2, negative 1. So not quite. With negative 1, it's going to be 1, negative 1, 2, negative 2, negative 8, and then 8. And that makes it just worse. Nine. So, no. There are no rational roots. This is all going to be irrational. Possibly going to be complex as well. We could also try just plugging in like I and negative I, because those would be nice. If it's not that, then it's going to split up as two different parts, our real and our imaginary, and we've got to take that separately. So, yay, good times. Right, we can always go over to Wolfram. Which is factor x cubed minus 6x squared. What was it? Nope. Plus 3x squared. Minus 6x plus 1. Factor complex. Nope. Right. So it looks like this does not even have nice values that we could figure out in the complex plane. It's just going to be numerical. Oh, wait, no. Sorry. These are real numbers. It seems like we don't have any particularly nice roots that we're working with here. Do we have exact value? We don't have it here. Nope. Exact form. Haha. Oh. Well, no wonder they don't want to send it to me or show it to me. This is likely not a textbook problem. I had actually done this in class just to throw up some like initial stuff on how to do it. I think this was like a last minute problem where I was just like, we've got 2 minutes, let's just explain how to do it without actually going through the steps of doing it because we don't have time. Factor when possible. Then use partial fraction decomposition. Right, so with partial fraction decomposition, this works really nicely. Or not this one, but generally the process works very nicely. You end up with some good terms, which end up cleaning up pretty well. We got time. Let's do one that actually works. So y double prime plus 4y is equal to 1 again. So when we take the LaPlace transform of both sides, again, we're doing this with the mind that later this will be discontinuous. So we'll look at that on Monday. Right, so again, this is going to be s squared big Y of s plus 4 y of s. It's going to be equal to 1 over s. Move that around again. This is going to be y at s times s squared plus 4 is equal to 1 over s. This y at s is going to be equal to 1 over s times s squared plus 4. Okay, and then we want to do partial fraction decomposition to break this thing down. So we say that 1 over s times s squared plus 4 should be equal to some a constant over s plus we want s squared plus 4, which is unfactorizable in the reals, to end up being in the denominator. In theory, you could do this over complex and just have two separate complex terms. Sure, why not? But here, it's oftentimes just easier to work in the reals. So bs plus c. So if we have a quadratic term in the denominator, we can have up to a linear term in the numerator in order to discuss how these all get broken down into separate individualized terms. Makes things a bit easier. All right, if we multiply everything by s times s squared plus 4, then we end up with 1 is equal to s over s goes away, so we get a times s squared plus 4 plus parentheses bs plus c times s squared plus 4, top and bottom is gone, and so we're just left with s. So 1 is equal to a s squared plus 4a plus bs squared plus cs. Alright, so this is saying that a plus b parentheses s squared must be equal to 0 s squareds on the left. Linear terms, cs equals 0 s's. That's all we got. There's only one. And other term, 4a is equal to 1. So a is going to be equal to 1/4. Here, c is going to be equal to 0. Here, we've got 1/4 plus b has to be equal to 0, and so b has to be equal to negative 1/4. So with that, this is going to be, wait, aha, back over here. So this is going to be 1 over 4s and minus 1 over 1s. Sorry, so that's an s over parenthesis, no, 4 times s squared plus 4. Alright, so then we do an inverse Laplace on each side. So again, this is inverse Laplace of y of s is just going to give us lowercase y of t. That's an easy one. And then we want to do an inverse Laplace on 1/4 times 1 over s. Again, our constant is going to come out. Minus a same deal, really. So 1/4 times the Laplace transform of s over s squared plus 4. Okay, so that's not where that is. Oh. There we go. List of Laplace transforms. I posted, or I didn't post this yet. Here. We're looking to go backwards. So we want to know which Laplace transforms have in the Laplace S domain. Let's see, 1 over s, we already know that, that's 1, so that's easy enough. That's going to be a 1/4 times 1, so just a 1/4. Okay, minus 1/4 times, this is now s over s squared plus 4. So if we look, what has s over a quadratic? Alright, I've got omega over s squared plus omega squared, or s over s squared plus omega squared. So both of those are a thing. It turns out that s over s squared plus omega squared is cosine of omega t. And then we don't worry about the u's just yet. Those who have maybe noticed that there's a u in there. So inverse Laplace is going to be negative 1/4 times cosine of its square root of that particular number, so 2t. Get rid of that 1 there. Now I did skip a couple of steps, I guess, up here, in that we also wanted to say that y at 0 was equal to y prime at 0, which was 0. Right, so this would have minus s times lowercase y at 0 and minus y prime at 0. And then here we'd also have a minus y at 0. So all those are 0. We just kind of you know, I didn't state it, which is my fault. I should always state it out loud. It happens. Okay. So this is going to be a 1/4 minus 1/4 cosine of 2t. And if we look at that in the original function, right, we're going to get, if we take any derivatives of 1/4, they're gone. And then if we take the second derivative of y here, first derivative takes a 2 out, second derivative takes another 2 out, so that's going to be 4 divided by 4. The first derivative of cosine is negative, which makes this term positive, and second derivative makes it cosine again, but it's going to be positive. So if we want to check real quick, right, this is going to be second derivative was cosine of 2t plus 4 times y. So the 1/4 minus 1/4 cosine at 2t. Does it equal 1? Here's, again, something that's not really surprising. Yes, it does. Right, this is going to get us 4/4, which is 1. This is going to get us, no, minus. A minus cosine at 2t. And here we had a cosine of 2t to begin with. Right, now, even with the partial fraction decomposition, I think I actually find this a little bit faster than going to the spring solution, which ends up you know, taking our homogeneous solution, so we set it equal to 0 first, and find the values that this is going to be nice with, which get us the sine and cosine of 2t. Then go through and find the non-homogeneous portion, which is going to again be 1. So we say, okay, what's that going to be on the other side? It's a constant. Maybe we try to put a couple, you know, another 1 or 2 orders in the polynomial, but it doesn't do anything, right? We just end up with a 4th. Yeah, essentially you're setting all of this stuff equal to just, or the solution to all this, just equal to c. Yeah, 4 times what number is going to get us 1? It's just a quarter. Our y double prime ends up being 0 when you have no other terms to it. And again, you go with a higher degree polynomial, it's still going to filter back down to just a quarter. And then you have to go back and plug in all of the values in for t, your zeros, into your y function to get your a, b, and c, well, a and b, c1, c2 off of our sine and cosine functions. In this case, we didn't even have a sine function pop out. We found the homogeneous solution and the inhomogeneous solution all in one go. Capital Y of t was equal to 0. So there isn't really a capital Y of t. Capital Y of s was equal to 1/4 1 over s minus 1/4 s over s squared plus 4. And then we do the inverse Laplace on those, and it ends up with just these functions. So 1/4 and negative 1/4 cosine of 2t. Let me know if that's what you meant. Bottom equation is a tautology. Oh, yeah. So that was just testing, right? We plugged in, what if we plug in y of t back into the original differential equation? Does that actually work, right? This is just a test to see whether or not our y of t was in fact complete. Yeah. Right, so we just wanted to make sure it worked. Yeah, let's just highlight this other thing real fast here, right? Because if we went with ew. Right, do the regular second order process. We say that y double prime plus 4y is equal to 0. Let y equal e to the rt. We did lambda because we were talking eigenvalues, but nonetheless. Right, so y double prime is going to be equal to lambda squared e to the lambda t. So this is going to be lambda squared plus 4 is equal to 0. So therefore, lambda is equal to plus or minus 2i. We know that our homogeneous solution, or in other words, our null space solution, is going to be equal to c1 cosine of 2t plus c2 sine of 2t. Right, so we had said earlier when we were doing our second order stuff, the complex value that you get out of this, in this case 0 plus or minus 2i, is going to determine what you get for your e to the blank t times your cosine 2t plus sine of 2t. And again, c1 here, c2 there. Which two? Yeah, no, up there. Right. So if you did your regular second order process, we got the homogeneous solution, the null space solution, doing this stuff. Right? And then we say, okay, cool. We want the non-homogeneous. Which is y double prime plus 4y equals 1. And again, assuming that this is not a discontinuous function, we're just going to say it's a constant, right? Let y equal c. That's it. So y double prime is going to equal 0. So you just get 4c is 1. So c is 1/4. And so that becomes y, it's not particular, general, is going to be equal to c1 cosine of 2t plus c2 sine of 2t plus 1/4. Then we say that y at 0 is going to be equal to y prime at 0 is going to be 0. So y at 0 is going to set our sine equal to 0, or not set, but it's going to allow our sine to be equal to 0 And so we've got our C1 times cosine of 0 is just 1. So C1 plus a fourth is C1 plus 1/4 is equal to 0, and therefore C1 is negative 1/4. Then you take a first derivative, you get 2 C1 sine, that's a negative of 2t, plus 2c2 cosine of 2t is equal to 0. The 1/4 just goes away because it's the first derivative, and then this has to equal 0. So our C1 term is wiped out from the sine function. Our C2 term is going to end up being 2c2 equals 0. So therefore C2 is equal to 0. Therefore there's no sine term in the first one, and then you end up with the solution that we set up above. All right, so now we know that y particular is going to be equal to, this is negative 1/4. Yeah, negative 1/4 cosine of 2t plus 1/4. Right, so like, I don't know, which one do you like better? They take up about the same amount of space, and in the LaPlace transform, it's just like a natural part of this stuff just kind of pops out. In our regular second order process, you have to like especially go through the null space solution for the harmonics, and then the non-homogeneous solution for the forcing function. And so it ends up being like two different ways to do it, which work, but at the same time, like, you know, in this case, neither one really takes any more or less time. It's kind of like, what do you want to do? Right? If you like partial fractions, LaPlace transforms probably for you. If you prefer just doing the null space and non-homogeneous portions separately, then, right, that process is perfectly acceptable. It does become a little bit harder sometimes if you just happen to forget that, oh, I need a particular solution for this thing. Again, LaPlace transforms, it's all part of the same process. It doesn't matter. You don't have to stop somewhere and say like, oh, let's set it equal to 0. I can't tell you how many times I initially plugged in my initial values for the null space solution without finding the, to find C1 and C2. Right? That's not how that works. You need that plus 1/4 on the end in the general solution in order to say C1 and C2 will be this, because that 1/4 is already taking care of something. Well, thank you, Omnifidus. I like that one. It uses all of the different little pieces. Okay. So we're going to wrap it up here tonight. We're going to find somebody to raid. And let's see if we have somebody doing math. We got Stats in the Wild. He's been up for 3 hours already, so maybe he's kind of winding down. Apologies for sending you over there last time, because as it turned out, he was in a meeting. Whoops. That's all right. All right. So it looks like Irish John Games is the only one who's doing something mathy-ish. He's been doing Rise of Piracy game development. Yeah. Oh, you know what? Maxi, is doing some software game development as well. She is... Come get your yap injection. Using Rust. There we go. So anybody who's interested in Rust, we're going to go see Mostly Maxi. I will see you. Anybody who's interested, come in on Friday, and we're going to be doing gamey type stuff. We'll see where we're at in terms of which game we're playing. I'm not sure exactly what it is yet, but we'll see. Also, we will be back on Monday and Wednesday for more differential equations. We are coming up pretty close to the end here, so we've only got, let me see, we're at 11:17. Yeah. I think this is going to be, next week is going to be the last week. So we're going to talk about unit step functions and how to use them in terms of differential equations, and heaviside function, all that stuff. And that's going to be it. So anyway, we'll see you all either on Friday for game type stuff or Monday, Wednesday for differential equations, and Tuesday for random math type stuff. So see you all later. My name is Obi.